Alright guys, so what I want to do is give you a video of Heron's formula and kind of talk my way through it as we're doing this proof. So Heron's formula is up top here. You can see it for yourself. We know that S is a semi-perimeter. So it's nice because it gives us an explicit formula for the area based on just knowing the sides. We don't have to mess around with finding the height. And in particular cases like this one, for instance, that's pretty useful. Cuts down on the amount of work. So what we start with every proof is a let statement. In this particular case, this is a big long let statement, and all it's really doing is describing what's going on in this diagram that I constructed. So if you construct the diagram and say, hey, let the diagram be given, that's good enough for me. So in that diagram, we've created two different right triangles. The larger right triangle, which we would call ACD, and the smaller right triangle, which we would call triangle BCD. So based on those being right triangles, we know we can use Pythagorean theorem, so let's go ahead and do that. So we would say by Pythagorean theorem, we know that we can say a couple different things. Number one, h squared plus this base of the whole thing, so that quantity c plus x squared, is going to equal b squared. The next thing is we want to deal with the smaller triangle, and we're going to use Pythagorean theorem again. So here we know that h squared plus x squared is going to equal the hypotenuse of that smaller one, which is a squared. So we got a couple different equations going on. I'm going to simplify a little bit. I'm going to solve for h squared in both of these, and we'll use that simplified version when we go to kind of plug some stuff in. So this will end up being minus the quantity c plus x squared, and this one turns into h squared is a squared minus x squared. So what we can do now is we've got this formula for h squared, so we'll just plug that up here into this formula, and we can rewrite our expression using substitution. So substituting, I'm going to abbreviate a little bit here because my pen's not real great, but we end up with something that looks like this: a squared minus x squared equals this quantity over here, b squared minus c plus x squared. Simplify a little bit, so we want to expand this binomial here. We end up with a squared minus x squared is equal to b squared minus, this thing is going to be c squared minus 2cx minus x squared. So the next step here is we're going to solve for x, so that then we can go up here and we can plug it back into this formula, and we can find an explicit formula for h in terms of all side lengths. So let's go ahead and do that. Simplifying this, that drops off and that drops off. Let's move all of our terms over that we can. So a squared minus b squared plus c squared is going to equal negative 2cx. And then dividing by negative 2c, we end up with a squared minus b squared plus c squared over negative 2c. And that's our expression for x. All right, so the next thing we want to do is we want to take this expression for x and we want to plug it up here for x, and that'll allow us to get an expression for h in terms of nothing but side lengths. You notice this is all in terms of a, b, and c, so we're going to have a squared minus this thing squared, and now we've got an expression for h in terms of all side lengths. A squared minus this entire quantity, so it's a squared minus b squared plus c squared over negative 2c squared. Simplify that a little bit, and so we're going to go ahead and take the square root, and now we've got our expression for h. That whole thing squared. So that's the first part of it. We've got an expression for h, and the second part will be using this expression for h to plug into our area formula. So check out video number 2 if you want to see part number 2 of the proof.